and welcome back to the Comptia Network Plus course, Frame Relay Technology. Frame Relay is a WAN technology in which variable length packets are transmitted by switching. Packet switching involves breaking messages into chunks at the sending device. Each packet can be sent over any number of routes on its way to its destination. The packets are then reassembled in the correct order at the receiving device. Because they are packet switched and the exact path is unknown, we use a cloud when creating diagrams to illustrate how data travels through this type of service. From everything you've learned so far, just telling you that frame relay is a packet switching technology should make you immediately realize a couple of things about it. Frame relay doesn't work like a point-to-point lease line, although it can be made to act like one. Frame relay is usually less expensive than lease lines are, but there are some sacrifices to make to get that savings. So why would you even consider using frame relay? Take a look at figure 16.6 to get an idea of what a network looked like before frame relay. Now check figure 16.7. You can see that there is now only one connection between the corporate router and the frame relay switch. That saves some major cash. Let's say you need to add 7 remote sites to the corporate office site and you have only one free serial port on your router. Frame relay to the rescue. Of course, I should probably mention that you now also have one single point of failure, which is not good, but frame relay is used to save money, not to make a network more resilient. Coming up, I'm going to cover the frame relay technology, information you need to know about when studying for the Comptia Network Plus exam. Committed information rate. Frame relay allows for a packet switch network to be provided to many different customers at the same time. This is really good because it spreads out the cost of the switches among lots of customers. But remember, frame relay is used on the assumption that all customers won't need to transmit data constantly or even all at the same time. Frame relay works by providing a portion of dedicated bandwidth to each user, and it also allows the user to exceed their guaranteed bandwidth if resources on the telco network happen to be available. So basically, frame relay allows customers to buy a lower amount of bandwidth than they really use. There are 2 separate bandwidth specifications with frame relay. Access rate, the maximum speed at which the frame relay interface can transmit. Committed information rate, CIR. The maximum bandwidth of data guaranteed to be delivered in reality if there's the average amount that the service provider will allow you to transmit based upon what you purchased. If these two values are the same, the frame relay connection is pretty much like a leased line, but they can actually be set to different values. Here's an example. Let's say that you can buy a rate of T1 1.544 Mbps and a CIR of 256 kbps. By doing this, you're guaranteed that the first 256 kbps of traffic you send will be delivered. Anything beyond that is called a burst. Transmission that exceeds your guaranteed 256 kbps and can total any amount of the T1 access rate if that amount is permitted in your contact. If your combined burst rate, which is the basis of your CIR, and excess burst size known as the maximum burst rate MBR exceed the access rate, you can pretty much say goodbye to your additional traffic because it's most likely it'll be dropped. Whether this means or not basically comes down to the subscription level offered by a particular service provider. In a perfect world, This always works beautifully, but remember that the little word guarantees, as in guaranteed rate of 256 kbps to be exact. This means any burst of data you send that exceeds your guaranteed 25 kbps will be delivered on something called a best effort delivery basis, or maybe not. If your telco equipment doesn't have the capacity to deliver it at the time you transmit it, then your frames will be discarded and the DTE will be notified. Timing is everything. You can stream data out at 6 times your guaranteed rate of 256 kbps T1 only if your telco has the capacity available on its equipment at that moment. Virtual circuits. Frame relay operates using virtual circuits as opposed to the actual circuits that leased lines used. These virtual circuits are what link together the thousands of devices connected to the provider's cloud. Frame relay provides a virtual circuit between your two DTE devices, making them appear to be connected via a circuit when in reality they're dumping their frames into large shared infrastructure. You never see a complexity of what's actually happening inside the cloud because you only have a virtual circuit, and on top of all that there are two types of virtual circuits: permanent and switched. Permanent virtual circuits, PVCs, are by far the most common type in use today. What permanent means here is that the telco creates the mappings inside its gear, and as long as you pay the bill they'll remain permanently in place. Switched virtual circuits, FVCs, are more like phone calls. The virtual circuit is established when data needs to be transmitted and is taken down when the data transfer is complete. Data link connection identifiers. Frame relay PVCs are identified to the DTE end devices by the data link connection identifiers, DLCIs. A frame relay service provider typically assigns DCL values, which are used on frame relay interfaces to distinguish between different virtual circuits. Because many virtual circuits can be terminated on one multiple frame relay interface, many DLCIs are often affiliated with it. Let me explain. Suppose you have a central HQ with 3 branch offices. If you were to connect each branch office to HQ using a T1, you would need 3 serial interfaces on your router at HQ, one for each T1. Simple, right? Well, suppose you use frame relay PVCs instead. You could have a T1 at each branch connected to a service provider and only a single T1 at HQ1. There would only be 3 PVCs on the single T1 at HQ, one going to each branch, and even though you'd have only a single interface and a single CSU DSU, the 3 PVCs would function as 3 separate circuits. Point-to-point protocol. Point-to-point protocol is a data link protocol that can be used over either synchronous serial dial-up or synchronous serial ISDN media. It relies on link control protocol LCP to build and maintain data link connections. Network control protocol NCP enables multiple network layer protocols, routed protocols, to be used on a point-to-point connection. Because high-level data link control HDLC is the default serial encapsulation on Cisco serial links and it works great, why in the world would you choose to use PPP? Well, the basic purpose of PPP is to transport layer 3 packets across a data link layer, point-to-point link, and it's non-proprietary. So unless you have all Cisco routers, you need PPP on your serial interfaces because the HDLC encapsulation in Cisco is proprietary. Remember Plus, since PPP can encapsulate several layer 3 router protocols and provide authentication, dynamic addressing and callback, PPP could actually be the best encapsulation solution for you over HDLC anyway. Figure 16.8 shows the PPP stack compared to the OSI model. Now, PPP contains 4 main components: EIA, TIA, 232C, V.24, V.35 and ISDN, a physical layer international standard for serial communication, HDLC, a method for encapsulating datagrams over serial links, LCP, a method for establishing, configuring, maintaining and terminating the point-to-point connection. It also provides features such as authentication. NCP, a method of establishing and configuring different network layer protocols for transport across the PPP link. NCP is designed to allow the simultaneous use of multiple network layer protocols. 2 examples of protocols here are Internet Protocol ICP and Cisco Discovery Protocol Control Protocol, CDPCP. PPP protocol stack is specified at the physical and data link layers only. NCP is used to allow communication of multiple network layer protocols by identifying and encapsulating the protocols across a PPP data link. Link Control Protocol LCP, configuration options. Link Control Protocol offers different PPP encapsulation options, including the following: authentication. This option tells the calling side of the link to send information that identify the user. The 2 methods for this task are PAP, AAP and CHAP. Compression. This is used to increase the throughput of PPP connections by compressing the data or payload prior to the transmission. PPP decompresses the data frame on the receiving end. Error detection. PPP uses quality and magic number options to ensure reliable loop-free data link. Multilink. The Multilink option makes several separate physical paths appear to be one logical path at layer 3. This means that the 2 T1s running Multilink PPP would show up as a single 3 Mbps path to a layer 3 routing protocol. PP dial-up connection. PPP can be configured to call back after successful authentication. PPP callback can be a very good thing because it allows us to keep track of usage based upon access charges for accounting records and a bunch of other reasons. With callback enabled, a calling router client will contact a remote router server and authenticate. Predictably, both routers have to be configured for the callback feature for this to work. Once authentication is completed, the remote router will terminate the connection and then reinstate a connection to the calling router. PPP Session Establishment. When PPP connections are started, the links go through 3 phases of establishment as shown in figure 16.9. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing, subscribing. Thank you.